Hello everyone, welcome to class 14. So, today we will be talking about Bravais lattices, something that we sort of started in the last class. We said so to represent the symmetry of the material into a unit cell, it makes sense to actually select a unit cell which has certain constraints imposed on its axis, and these constraints we have actually derived from an underlying symmetry. We said if it is a monoclinic system, the constraints are that a couple of angles alpha and beta should be 90 degrees, gamma is not equal to 90 degrees, and the constraints kept on increasing as we kept moving towards cubic system and also trigonal systems, right. So, the rhombohedrals and the hexagonals. Now, there are cases where it turns out that you cannot really define a primitive unit cell. You have to actually such that the unit cell captures the symmetry of the system. We gave you I gave you an example of lattice which is like this, and I told you that the underlying symmetry of this lattice is at least two two-fold axis of symmetry, and so I am going to put lattice points there. However, if I select a unit cell which is of this sort, so here the axes are not perpendicular to each other, the alphas and betas are not equal to 90 degrees. So, if alpha is not equal to beta is not equal to 90 degrees, I would not immediately recognize that there is an underlying symmetry which is a two-fold which is two two-fold axis of symmetry or one mirror, right. So, rather what I would do then is to select the pink unit cell or this maroon unit cell as my unit cell, which this maroon unit cell, if you look at it, has more than one lattice points in there, and if I count the number of lattice points, there are 2 lattice points. But in the maroon unit cell, alpha equal to beta equal to 90 degrees. So, if I have an underlying symmetry which so I would not right away know just by looking at the lattice, I have to put the motif to understand that, but imagine that after putting the motif I have an underlying symmetry that has at least two two-fold axis of symmetry. It makes sense to actually define this as my unit cell of choice, right. So, this is the idea of centering a unit cell. So, because so there are more than one lattice point inside a unit cell. So, this is not a primitive unit cell, this is a centered unit cell, and the centered unit cell leads to the idea of what are called Bravais lattices. Okay. So, with that we will actually look at how many different kinds of centerings are there. So, if I have a unit cell which I give you, right. So, with certain so all unit cells need not be primitive in nature. So, if I need not be orthogonal, the axis of all unit cells need not be orthogonal. So, if I give you a unit cell which is somewhat like this with right, and I ask you to center it. So, A, B, C are the axis of the unit cell, alpha, beta, gamma are the angles, right. There are some constraints depending on the crystal system, and I ask you to center this unit cell. What are the different kinds of centerings that one can do? That one can do to a unit cell, right. So, so by centering I mean I am actually putting in lattice points inside this unit cell, right. So, and I am looking at a unit cell which has more than one lattice point. Okay. So, one of the centerings, I mean one of the more common centerings is what is called body center, body centering, or represented as I. I comes from a German word which I do not think I can pronounce, so I will just leave it as I. So, body centering in German starts with an I, and it starts with a word that starts with an I, right. So, we represent body centering as I centered unit cells, right. Now, what is body centering? If I have lattice points at so in the unit cell at all the corners of a unit cell. So, these corners are represented as so there is an origin, there is a body centering is so if my axes are A, B and C. So, by body centering I am going to put an atom at A plus B plus C by 2. Sorry, not an atom, pardon me, I should not be saying atoms, but I put a lattice point at A plus B plus C by 2, or in other words, so I have lattice points at 0 0 0 and half half half, right. So these are the positions of my lattice points, but so I can also have lattice points at 1 0 0, but because of translational symmetry, right, 1 0 0 is exactly the same as 0 0 0. So I do not need to write 1 0 0 or 0 1 0 or 1 and so on and so forth, right. So all these by translational symmetry, 1 0 0 is a translation of 0 0 0 by a lattice vector. Okay, so let me just write it this way: 1 0 0 is a translation of lattice vector, translation of point 0 0 0, lattice point 0 0 0 by a lattice vector A, right. So I do not really need to write 1 0 0, because the assumption is in a unit, if I am defining a unit cell, I have translational symmetry, right. So I am just going to say that this unit cell has 0 0 0 and all its equivalent points, and half 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 and all its equivalent points, right. So these are the two different points I have. So in a lattice, in a body centered or eye centered lattice, there are two lattice points. Okay. That is the first kind of centering. Now, what is the second kind of centering? So, I mean, you may have studied about body centered cubic and face centered cubic lattices, right. So, second type of centering is what is called face centering. Okay. So, now, so there are 2 points for points per unit cell here. Then I have face centering. So, when I am face centering, I put points at 0 0 0, that is fine, but I also put points at half half 0, 0 half half, half 0 half. So, effectively if I have a unit cell like this, I am putting lattice points at all the centers of all the faces. So, these are okay. So, let me draw the lattice points in a different color. So, this is a lattice point, these are all the 0 0 0 points, right, and then I have a lattice point here, 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 here at all the face centers, right. So, so there are all these faces, right. So, 4 plus 2 6 faces, and the centers of all these faces are what are called face centers, and at all these face centers I have a lattice point, right. So, my lattice is now so this is so I can periodically expand this to get the entire lattice, but my lattice my unit cell now has 4 points in a face centered lattice, right. So, and face centering is represented as F, right. So, F for face center, that is English, that is not German. Okay. So, then we can also center the bases, right. So, instead of centering all the faces, we just center one face rather, that is called base centering. So, I center either this base or just one base, right. So, this is called base centering. Lattice point at the center of only one face, which means if I have 0 0 0, I also have half 0, that is it, right. So, 2 lattice points, or so this so if this is called, this is the C axis, this is the A axis, this is the B axis, right. So, this face that I have just drawn here is the B face, right. So, if I center these faces, the red faces, it is called B centered lattice, right. If I center the blue faces, that is perpendicular to the C axis, those are called C centered lattices. Okay. If I center the green faces, there is one more on the other side, I just do not want to confuse you, that is called A centered lattice. Right, but at any time I am just centering one base, right. So, only centering one base, right. So, I either have, so this is in general either B center or A center or C center is just called base centering, right. So, one of the bases you are centering. Okay. So, this is called base centering, okay, all right. So, next we have another, I mean, so we want to explore, okay. So, why one base, why not two bases, right. So, I can center so I can have so this has, okay. So, just one base centering has 2 lattice points per unit cell. So, why not two bases? So, in a face center, why not two faces rather? In a face center, I have centered all the 3 faces or all the 6 faces rather. I mean, I can center 3 faces and lattice translate it by one unit cell, that will center the other 3 faces. So it's I mean, so I can just talk about 3 faces, centering 3 faces. Okay. So, in base centering, I have centered one base or 2 bases in one entire unit cell, right. So, one base and lattice translated, that centers the other base also. But so I finished 1 and 3, why not 2, right. So, that is the question. So, why in this case, so can I have centered 2 bases, but not the third base, right. So, if I center 2 bases, the vectors, the lattice vectors I will have are 0 0 0, half half 0, and let us say I center something like 0 half half. Okay. So, I should have 3 lattice points per unit cell. Right. However, so I can just so this is vector v1, this is vector v2, this is vector v3, right. So, if v2 and if vi and vj are vectors in a lattice, are lattice vectors rather, let us just write it that way, right. Vi plus Vj is also a lattice vector. Okay. So, V2 is a lattice vector here, V3 is a lattice vector, are lattice vectors. So, V2 plus V3, which is equal to half 1 half, right, or I can just translate it back by one unit vector. So, minus 0 1 0, right. So, that will be half 0 half, right. So, if V2 plus V3 let us say minus 0 1 0, that is also a lattice vector, minus B. Okay. So, that should also, this also should be a lattice vector. Or there should be a point at the third face center also, right. If there are, if lattice is centered about 2 faces, translation symmetry would ensure that the third face is also centered. So, this will then turn out to be just face centering, it is nothing new, right. So, so you cannot have only 2 faces centered, right. It is either one face which we call as base centering, or you have all the 3 faces centered, and that is called face centering. Okay. So, yeah, so these are the different sorts of centering, and any other centering that you can think of, right. So, edge centering will be so you can actually prove that it will be one of these I or F or B that I just showed. Okay. So, it is going to be I centering or F centering or B. I mean, so B or so B for base centering, but so you can equivalently write it as A or C centering. So which face are you centering really, right. So, these are all equivalent. Okay. Okay. So, now let us see. So, these are the different types of centering that can exist in lattices, right. Okay. So, now why do we want to center a lattice? We want to center, why would we want to center a unit cell? We want to center a unit cell so as to retain the symmetry of the problem. Okay. All right. So, only then we will center. If retaining, if centering a unit cell is not going to add any additional benefit, then we will not center the unit cell. Okay. So, for example, let us go into triclinic system. Now, in a triclinic system, I have A not equal to B not equal to C. So, I am just going to draw something like that, and in general, so this is not equal to so the angles are also not equal, right. So that is my triclinic unit cell. So, I am going to draw this, this, this and this, right. So, this is my triclinic unit cell. Right. So, now let us center something, right. So, let us do a face center, or okay. So, let us do something easier than face center. Let us just center this face, right. So, let us do base centering. So, this is the C face is centered. So, this is C centered, right. Now, if it is C centered, what I can do is, okay. So, do I have any specific advantage? So, the question that I am asking is, do I get any specific advantage in representing the symmetry by centering, or in this case C centering the triclinic lattice, the triclinic unit cell. Right. So, what I drew in green is a primitive triclinic cell. Okay. So, does not matter. So, okay. So, if I center this, then so I can then I can define. So, the green cell, right. So it is a triclinic system. It is a triclinic system means the symmetries that I worry about are 1 or 1 bar, right. Okay. Now, if I define another unit cell like this, right. So, this is a centered unit cell. The green cell is a centered unit cell, right. Green cell is a C centered unit cell. Now, let me define, okay. So, the green one is my centered unit cell. So, I have additional lattice points which are C centered. Okay. Now, I am going to draw a primitive unit cell to see if centering has given me any sort of additional advantage, right. So, I am going to join this, I am going to join so that is going to be my centered primitive unit cell. Okay. So, there will be another point there, another centered point. So, I can draw a unit cell like that, right. Now, this unit cell, the blue unit cell, is a primitive unit cell, right. Now, this blue unit cell also does not have, so the green, so A not equal to B not equal to C, there are no particular constraints on A, B, C, alpha not equal to beta not equal to gamma not equal to 90 degrees, right. So, there are no particular constraints on A, B, C or alpha, beta, gamma, but even in my green centered unit cell, there are no constraints, right. So, that is okay, because so a green cell has no constraints, or it is not giving me any additional symmetry. So, just looking at green cell, I see that the system is triclinic, but looking at blue cell also I can say exactly the same thing, the system is triclinic, the underlying symmetries I have are 1 or 1 bar, right. So, there is no additional advantage by centering the triclinic unit cell, right. By centering a triclinic unit cell, okay, or let me put it this way, a centered triclinic unit cell does not offer any additional visualization into corresponding underlying symmetry. As its corresponding primitive cell. Okay. So, I could as well just define a primitive cell, so there is no need to just unnecessarily increase the number of lattice points, right, in a triclinic cell. So, there is no need to unnecessarily increase the lattice points and define centered cells triclinic cells, because there is no additional insights into symmetry that you are getting. Okay. So, it is 1 and 1 bar, that is it, right. So, even from a primitive cell I get the same information, even from non primitive cell I get the same information. Okay. So, as a result, so no one generally, I mean, so it is not, you do not center the triclinic cells. You may see in some papers that people do center them, but that is to represent some phase transitions or something like that. One triclinic cell is transforming to some other triclinic cell, and so then I can center it, right. But so just it is not a different Bravais lattice that you are creating, right. So, triclinic cells only are primitive in nature, primitive is P and triclinic is A, right. So, the only Bravais lattice I have from triclinic cells are primitive cells, only in triclinic's system is a primitive lattice, primitive cell, right. So, is primitive. Okay. So, I am going to represent that as AP, that is my first Bravais lattice, right. So, out of all the crystal systems, now I am going to classify them as 14 Bravais lattices, and the first Bravais lattice is my AP. Okay. No significant advantage of centering any the triclinic unit cell. Now, next we go to monoclinic cells, right. So, monoclinic system. What about a monoclinic system, right. So, now let me take for example, so a monoclinic system has, let us say my unit cells are like this. Right. So, in general these this angle is not 90 degrees, this is gamma not equal to 90 degrees, this is my c axis, okay, and then alpha equal to beta equal to 90 degrees. I am just going to represent one of them, alpha equal to, that is okay. So, that is beta equal to 90 degrees. Okay. So, alpha is also equal to 90 degrees, right. So, alpha equal to beta equal to 90 degrees, gamma is not equal to 90 degrees. Okay. And I am going to consider, just like I did in triclinic cell, I am going to consider a centered unit cell. I am going to center it about, this is C centering. Okay. And I am going to see if there is any particular advantage I get by C centering. Okay. Now, I can either draw it and show you here, but I would just very quickly show you on a PowerPoint presentation the same thing that I am going to show here. So, I am going to draw a corresponding primitive cell in green pen, right. So, so this is one axis, this is the other axis, and the third axis will be, well, it can be here. So, then it goes, yeah, so okay. So, the third axis can be here, and so this can also go this way, and I can finish the unit cell that way, right. So, okay, so I will just show you, it is better than me drawing. So, so this is so this is a primitive lattice and this is a centered lattice. So, I am attempting to C center it, right. Now, when I am C centering it, I can I am drawing a corresponding primitive lattice, which is what I attempted to draw there. But when I draw the corresponding primitive lattice, so these points are in the same plane as this, right. So, these are exactly in the same plane, right. Now, the primitive lattice is also monoclinic, because this plane is perpendicular to the c axis, right. So, you have in the primitive lattice alpha equal to beta equal to 90 degrees, gamma is not equal to 90 degrees. So, okay. So, primitive lattice is also monoclinic, centered lattice is also monoclinic. So, by monoclinic what comes to my mind is that, okay, so there should be a two-fold axis of symmetry or a two-bar fold axis of symmetry, which is my c axis, but the so I get the same information by looking at the corresponding primitive lattice, right. So, not the so I do not need to center it, right. So, there is no need to center this monoclinic unit cell. So, I will go back, yeah. So, I am drawing some other unit cell, but okay. So, I can also correspondingly define my unit cell just like what they did, which is here, right. So, something like that, there will be another point there. So, this green primitive cell also has alpha equal to beta equal to 90 degrees, gamma is not equal to 90 degrees. So, no need for C centering. My primitive lattice itself gives me unit cell itself gives the necessary information, all the necessary information about underlying symmetry. Okay. So, there is no need for C centering in monoclinic lattices, there is going to be no C centering. But what about so how about B centering or A centering, right. So, let us look at that. If I center this is the B face, right. So, in this case you can see that the B face is centered. So, if the B face is centered, however, and I draw a corresponding unit cell, a primitive cell, as you can see here, this primitive cell is not monoclinic anymore, right. So, here alpha is not equal to beta, that is okay, that is not equal to 90 degrees. But by centering the B and then drawing this lattice vector, I have made sure that gamma is also not equal to 90 degrees, right. So, the unit cell, the primitive cell that I have defined is has a property. I am not saying the system is not monoclinic, but the primitive cell has a property that alpha is not equal to beta, is not equal to gamma, not equal to 90 degrees, right. So, looking at the primitive unit cell, I will keep it, but I am going to say here in my notes that you may want to refer to the supplementary slides. Right. So, in the what I showed there is if I B center the monoclinic cell or the monoclinic, let us not worry about the unit cell, right. The corresponding primitive lattice, the monoclinic unit cell, okay. Has alpha not equal to beta, not equal to gamma, and that is sorry, yeah. So, that is not equal to 90 degrees, right. Whereas, in a monoclinic cell you want alpha equal to beta equal to 90 degrees. This is what a monoclinic cell should be, right. I am going to write it in red, alpha equal to beta equal to 90 degrees in a monoclinic cell, right. So, but just by hence by looking at the primitive cell, I cannot infer the underlying symmetry, right. So, the underlying monoclinic symmetry, I mean monoclinic symmetry meaning underlying two-fold or mirror symmetry, because I do not see my monoclinic unit cell, right. Okay. So, as a result the B centered monoclinic unit cells are a necessity, or so if I am using, so this is if or in other words B or A centered monoclinic unit cells are a necessity. You have to define centered monoclinic cells, okay. So, B or A centered. Now, so this is assuming, so here I am assuming that the C axis is the two-fold axis. Then I can have B or A centered unit cells are a possible, are a Bravais lattice, a possible Bravais lattice. But not C centered. Okay. Similarly, so if I use another convention where B axis is the two-fold axis, then I can have so A centering or C centering. This is convention 2, this is convention 1, right. So, you can define it based on so what you are used to in general. Okay. So, okay. So, now you can also look at if it is so if you can do a face centering or a body centering of monoclinic structures, and you will see that face centering or body centering will turn out to be one of the base centering, right. So, you can define a unit cell where face centering will exactly be like base centering, right. So, you can define a unit cell where body centering will exactly be like base centering, right. So, that I leave it for you to show it geometrically, but in general in a monoclinic system I will show it for a tetragonal system, right. So, in a monoclinic system, typically what you have are primitive monoclinic cells, that is one set of Bravais lattice, and the second one is a C centered monoclinic cell, right. So, sorry, a B centered or A centered monoclinic cell, base centered essentially, sorry. I have to write it as MB, M for monoclinic and B for what is the type of centering, right. So, a B centered or so equivalently to this is A centered or C centered depending on the convention that you are using. Okay. So, these are the two types of centering that I can have. So, as a result, so far I have had TP, MP, MB, right. So far I have defined 3 different Bravais lattices and I have to define 14, right. So, I said that I am going to show that there are 14 such Bravais lattices, right. So, in a monoclinic structure it does not make any sense to define a body center or a face centered lattice. So, the only things that exist are MP and MB, not even MC, right. So, MA or MB are equivalent, but not even MC, but MP or there is no MF or anything like that, right. Okay. So, now we will go towards the other symmetry, which is orthorhombic symmetry. So far we have come to define 3 different Bravais lattices. Now, what about an orthorhombic symmetry, right. Orthorhombic let us say crystal system. Now, in an orthorhombic crystal system I can have so there are going to be no constraints, you can actually go and prove that to yourself. So, I can have systems that are primitive, right. So, I have O for orthorhombic, OP for O primitive orthorhombic. I can have B centered or correspondingly A centered, correspondingly C centered orthorhombic. In earlier case, so these are similar because these are all base centers, but I can have only B center or A centering, right. So, here I can have all the 3 centering, right. So, all of them so are essentially, so to define the orthorhombic symmetry. Then I can also have F centering and I can have I centering, right. So, all these things will exist. So, orthorhombic system contributes to 4 different Bravais lattices. Okay. So, now in the laundry list of things we next look at tetragonal system, and so in the tetragonal system so if I C center a tetragonal system. So, tetragonal system is A equal to B, these two are equal and the angles are 90 degrees everywhere, right. So, if I C center a tetragonal system, so this is my C centered unit cell, the red one, right. That one and that one, right. So, the red unit cell is a C centered tetragonal cell. But I can also since A equal to B, right. So, I can also try to just define a primitive unit cell, and primitive unit cell I am going to redraw it whatever they have drawn in this color, right. So, this is going to be a corresponding P cell. So, I can redefine the unit cells, but I am not losing any tetragonality. So, in the primitive unit cell is also tetragonal. That is because this that is a square, right. So, in the initial so in a C centered cell we took the base as a square, right. So, A equal to A, right. Now, in a square if I just look at, if I draw another primitive cell like this, right. So, this will be A by square root 2, but this is also A by square root 2, and A by square root 2 can identically be taken as A dash, right. So, that is the lattice parameter of your primitive cell, P cell, and so the angles are also 90 degrees, right. So, you have not compromised on any sort of thing, so in going back to a primitive cell from a C centered cell. So, as a result, so having a P cell or having a C cell is equivalent to having a P cell, right. P is more simple, P has only one lattice point. So, I am just going to define a PT, right, which is yeah. So, I am just going to define a tetragonal system with which is just primitive. Similarly, you can look at this exercise that is done here. F, which is a face centering, will be identical to a body centering, right. So, in a tetragonal system, so I am going to keep this and I am going to write it here. So, in a tetragonal system, I have P is identically equal to C, right, or C centering, and similarly, so I do not specifically need to do any C centering, that is the same as primitive cell. Similarly, F is identically equivalent to I centering, right. So, I would rather take the simpler of the two and then say that I have only two Bravais lattices in a tetragonal system. Okay. So, one is a primitive lattice T p and the other one is T I, which is called the body centered tetragon, because I is simpler than F, because I has two lattice points, right. Okay, wait one second. T I, right. So, these are the two Bravais lattices. Now, P has one lattice point. So, whenever I have to choose between P and C or P and anything else, so choice between anything else, any other centering, P wins, right, because P is a simpler lattice, I have a simpler unit cell. So, I have only one lattice point inside, right. Whereas, if I have a choice between I and C, sorry, I and F in this case, right. So, then I am going to select, I choose I, sorry, this I, this is me I, choose I, which is the body centered I, as a suitable Bravais lattice. So, I am going to call tetragonal unit cells which are face centered also as body centered tetragonal unit cells, and I will define an appropriate body centered tetragonal unit cell, because that is simpler as a suitable or preferred unit cell with only, because I is simpler in the sense that I has only two lattice points, whereas F has 4 lattice points, F has 4 lattice points. Unless absolutely necessary, I will not define F, right. So, 4 lattice points. Okay. So, I have two Bravais lattices. Now, let us again, so far what happened, number of Bravais lattices so far. Okay. So, let us summarize. So, I have one from the tetragonal from the triclinic system. I have MP and MA or MB or MA depending on so what is what's your convention. Then I have I have OP, OB, OA, OC, OF, OI, right. So, this is 1, this is 2, this is 4, and then I have TP and TI. Okay. So, this is 2. So, 1 plus 2 3, 5 4 9, so far 9 by 14, right. So, I will stop this class at 9 at listing out 9 Bravais lattices out of 14 that we have, and in the next class I am going to go into the cubic systems and the trigonal systems, where we finish the list of 14 Bravais lattices and then move on into point groups. Okay. See you in the next class.